Hi, my name is Kristina Theodosopoulos, and the title of my project is Noise-Hardened BBA4, Quantifying and Mitigating Environmental Noise to Restore a Secure Key in Classroom-Scale Quantum Key Distribution System. Classical encryption methods such as RSA and ECC secure global communications today, but advances in quantum computing threaten to break them completely. Quantum key distribution, QKD, provide a physics-based alternative that is not vulnerable to increased computational power. However, environmental noise and system imperfections can raise the quantum bit error rate, QBER, preventing secure key generation. As a result, reducing QBER is one of the most primary barriers to deploying QKD in real-world environments. Light polarization must be first introduced to understand this project. Light is an electromagnetic wave, and polarization describes the orientation of its electric field, which can be linear, circular, or elliptical, as shown in figures 2 and 3. Perpendicular polarization directions, such as horizontal and vertical or diagonal pairs, can be clearly distinguished and precisely measured. For this reason, polarization light provides a natural physical system for encoding qubits. In classical computing, information is stored in bits that are either 0 or 1. A qubit, however, can exist in a superposition of both states, which is mathematically represented as a combination, as shown in figures 4 and 5. These states can correspond to physical bases such as horizontal and vertical or diagonal polarization, as long as they are perpendicular. When a qubit is measured, it collapses into one definite state, with probabilities determined by the amplitudes alpha and beta. In this project, photon polarization states act as physical qubits, enabling secure quantum information encoding. For this project, the BBA4 protocol, a form of QKD, was used that often is explained using Alice, Bob, and Eve. Alice encodes bits into photons while Bob randomly selects a basis to measure each photon, and only matched bases are kept to form a shared secret key. However, environmental noise such as ambient light and reflection can introduce errors, increasing the QBER and limiting real-world reliability, as shown in figure 8. The purpose of this experiment was to evaluate how environmental noise impacts a low-cost BBA4 quantum key distribution system and determine whether secure key exchange is possible outside of controlled laboratory settings. The alternative hypothesis was that with properly designed layered mitigation strategies, the system can maintain the QBER below the security threshold even under high ambient light conditions. In Phase 1, the core BBA4 optical setup was constructed as shown in Figure 9, transitioning from the initial alignment stage to a functional polarimeter. A 520 nanometer green laser served as a single photon source substitute, while the optical components shown in Figure 10 were used to prepare and measure polarization states. The half-wave plate enabled precise rotation of polarization, and the beam splitter separated horizontal and vertical components. Photodiodes converted detected light into voltage signals to determine whether light was transmitted or reflected. QBER was calculated by comparing transmitted and received bits under matching measurement bases. This diagram outlines the full QKD setup. Figure 12 shows the setup with no eavesdropping. In blue, Alice is setting the light in her chosen polarization states. In yellow, Bob is set up to receive the photons. In the eavesdropping setup, blue and yellow show Alice and Bob again, but in red there is Eve. Eve receives Alice's light and also randomly chooses her bases. In controlled trials without eavesdropping, matched polarization bases produce 100% bit agreement, confirming correct system alignment. When intercept resend attack was introduced, bit discrepancies appeared. The average QBER was 20.6%, which is close to the theoretical value of 25%. As shown in tables 1 through 3, the clear increase in QBER demonstrates that the system was able to reliably detect eavesdropping. In Phase 2, environmental noise was investigated. As shown in figures 13 through 15, the system was tested under dark conditions, typically classroom light, bright artificial light, daylight, and directed glare to evaluate how increasing ambient lux affected QBER. A baseline calibration was first performed. Reflection effects were then isolated by introducing different surfaces at fixed lighting levels, including a matte blackboard, a glossy whiteboard, a mirror, to distinguish absorption. Ambient light was the dominant source of noise. Under dark conditions, QBER remained near 2%, and the system stayed secure under normal classroom lighting. However, above approximately 1200 lux, QBER exceeded the security threshold, and secure key generation failed. Reflective surfaces further increased error, demonstrating that unfiltered ambient light severely limits practical quantum key distribution. In Phase 3, mitigation strategies were implemented to reduce environmental noise identified in Phase 2. Spatial filtering used a pinhole aperture tube to block off axis light, while a 520 to 532 nanometer bandpass filter provided spectral isolation of the laser wavelength. Temporal filtering was achieved through Arduino-controlled gate detection, and a polarization alignment was optimized using wave plates and matched analyzer bases. Temperature effects were monitored, and an ablation study evaluated the contribution of each component. Each mitigation layer produced a significant reduction in QBER. Without filtering, QBER averaged 19.6%, while a full mitigation system reduced errors to 3.1%, an improvement of approximately 84%. Temporal gating produced one of the largest reductions, and temperature was found to have a minimal impact on the performance. The results demonstrated that layered mitigation is essential for maintaining secure QKD in realistic environments. Temporal gating proved especially effective, reducing QBER from 9.8 to 4.9%. The sequential ablation study confirmed that each mitigation layer contributed independently, with the QBER increasing stepwise when filters were removed. Temperature testing showed that thermal effects played a minor role compared to optical noise. As visualized in Figure 20, the ablation study was successful and kept QBER below the 11% security threshold across broad range and ambient light conditions. Several limitations were identified during this study. Ambient lighting conditions were difficult to keep perfectly constant, and variations in classroom brightness introduced fluctuations in background photon count. Additionally, polarization drift occurred because long trials had temperature changes in small shifts in optical alignments. Future studies could address these limitations by implementing a single photon source to more accurately model the quantum-limited BB84 performance. Automatic polarization stabilization could be introduced to correct drift in real time, reducing manual interventions. In conclusion, this study demonstrates that a BB84 quantum key distribution system can function securely under realistic classroom conditions. While eavesdropping and unfiltered ambient light significantly increased the quantum bit error rate, these effects were clearly detectable and quantifiable. The implementation of a layered spatial, spectral, and temporal filtering reduced QBER by over 80%, restoring secure key in exchange even in bright environments. These results support the alternative hypothesis. Thank you for listening. These are my references.